So here's the model. You got the nichrome magnets ascending through the tube, and we could draw the dipole field. We'll do that later, okay? You know how to construct that for two electric charges. You just kind of assume two equal and opposite magnetic charges and get the field, the way you've sketched fields during the first week or so.
Where would those charges be located on the magnet?
Wherever. That's a tricky question, and nobody's done the algebra that I asked them to do on this problem about a week ago. Okay? So I'm not going to tell you. Do the algebra, then we'll talk about it. Now, anyhow, we oversimplify by assuming a uniform magnetic field, so, and it's going to be a uniform magnetic field directly away from the axis of the magnet. Okay? Makes sense? And the magnet is falling with some velocity, v. Okay? Now, if that's the case, then as the magnet approaches this, now the magnet is, the tube is a cylinder, so we're going to assume the magnet is cylindrical. It doesn't really have to be, okay? And we're going to assume this is a cylindrical region here with a constant magnetic field, sort of equal to the average magnetic field, okay? So what happens when the magnetic field crosses this thing? The flux changes, right? Okay, so what's the average? So what's the average rate of change of the flux? Is a region passes this circle. Okay?
Does that circle have a height?
It's some position along the tube. You know how fast the thing is moving. If you know the dimensions of this region and the magnetic field, yeah, okay. So this region's got to have some diameter, meaning it'll have some radius, and it'll have some thickness. So just a cylindrical region. How much does the flux change as this thing passes? The average rate of change of flux as this region passes the circle. That should give you the average EMF. Have I talked about EMF? Well, it's the number of joules per coulomb. Okay? Average number of joules per coulomb around a region of copper of the same dimensions. Well, not the same, yeah, a region all the way around the cylinder of this length.
Would S stand for field or for force?
Would what?
Would F stand for field or for force in EMF?
I'll tell you about EMF. You don't need that. It's called electromotive force, but it's not a force. It's the work per coulomb. And that's the rate of change of flux. Okay? Now, what that tells you then is the number of joules per coulomb around this little band of the tube. Okay? And then using this, knowing that this is copper, we can figure out how many newtons per coulomb. We can figure out the electric field around that circumference, because we know how many joules per coulomb when we know how far it is around. Okay? And if we know the thickness, which we can easily get by measuring its length, knowing that its inner diameter is a 1/2 inch or 3/4 of an inch, we can put it on a balance and find that it's got a mass of 386 grams. We can figure out how thick that thing is. Okay? So from that, from this distance and the thickness, we know what its cross-sectional area is, driving a current through that cross-sectional area. Now when I calculate this, I get currents in the thousands of amps, at least in the many hundreds. Okay? Doing various calculations in my head. I'm thinking, maybe 3,000 amps in a 1/2 inch tube. Maybe. That's assuming a 1 Tesla field. And I don't know that we have a 1 Tesla field, but it's a pretty strong field from the neodymium. Okay? So my point is that by looking at the rate of change of flux with this oversimplified diagram, because you don't have a clue how to do the integral of this thing. Okay? And as far as that goes, neither do I, except numerically, because it's not going to be a nice function. It's a dipole. Do the algebra in that expression I gave you. Okay? It's actually integrable. But when you get the, we'll do an oversimplified model. There's no field outside of here and an average field inside of here that's going to give you the same amount of flux. Okay? But you combine that with this, you can estimate the electric field. And then you can estimate the current. Now if you know the current in the number of joules per coulomb, you can figure out how much energy, which is heating the copper up. Then you get to think about, okay, how does this energy dissipate over the copper and how does it dissipate out into the room? Because we've got to deal with that too. Motivation to study thermal exchange, which is mathematically much like any other change. Along the copper wire, it's just a diffusion. All kinds of things diffuse. Most of you as engineers will have a transport course or something equivalent. So it'd be good to break the ice now and get some idea of what we mean by transport. Okay?